Alright, this is PowerPoint 4.5 and 4.6. 4.5 is pretty short. It's all on metallic bonding. 4.6, kind of long, but a lot of important stuff in it. So 4.5 metallic bonding, you can see here that there are electrons that are flowing around with protons being positive, causing a sea, quotes, of delocalized electrons. Um, these are strong forces between positive charge ions and these delocalized electrons, causing a strong attraction between the atoms. So a few things to remember about metal bondings. The outermost electrons, like most things that bond, wander freely through the metal. That's why you can have good conductivity of electricity. They act like glue, and they can move rapidly through the fields. Hence, they're good conductors. Um, these are good conductors of heat because there's free-flowing electrons that transmit kinetic energy. Energy can flow freely, therefore you can heat up your pasta pot or whatever dish you want very quickly if it's metal. And it's really hard to pull apart, to break, because of these electrons holding the um, atoms together. Um, atoms slip between each other, therefore they can be very ductile, which is very important to a lot of industry, especially with copper. So, a few things of properties: high melting points, high boiling points. These take a lot of energy to break, therefore you need a lot of energy to melt and boil. They conduct electricity, free-flowing electrons, and they conduct heat because of the movement of these electrons as well. Alright, 4.6, intermolecular bonding. So intermolecular forces. These are very important because it deals with a lot of properties of compounds. So in a molecule or compound, you have intra with an A, molecular forces. That's like ionic bonding, covalent bonding, metallic bonding. These are between atoms. Inter is between molecules. So how molecules actually hold on to each other. So how they boil, how they melt, how they freeze, which are generally pretty weak given that if you're dealing with covalent compounds. The first one we'll talk about are type of intermolecular forces. You have van der Waals forces. These are temporary dipole induced forces. Sometimes they're called London dispersion forces, mostly in covalent bonding. You have permanent dipole-dipole, meaning there is a strong attraction between a positive side and a negative side. Hydrogen bondings is a type of dipole-dipole, which are stronger. So you can see here, ionic compounds are by far the strongest. That's because it's a clear positive, clear negative atoms. OH bonds, it's type of hydrogen bonding. It's strongest of the hydrogen bonding, like in water. You can see hydrogen bonding is stronger than dipole-dipole, and the weakest is van der Waals forces, or VDW forces. So, the ability to attract a bond is electronegativity, which basically helps determine what type of intermolecular forces you're dealing with. So from this chart, you can see that the red, the halogens, oxygen, nitrogen, chlorines, are the highest electronegative, meaning they want electrons, which makes sense. And you can see the metals are very low in electronegativity because they give off electrons. They don't want electrons. They want to give it off. There are some discrepancies in a little bit in the transition metals. They go a little higher and then they dip back down and then back up. But in general cases, the highest is towards fluorine. So as you saw, increased electronegativity is the atom's attraction for the electrons itself. Basically, you move from the left to right, they increase, and as you go up the group, they increase as well towards fluorine. So if you remember fluorine as the most electronegative, you can figure out the pattern pretty easily in general cases. You can see boron is the least electronegative all the way to chlorine, because chlorine is the top of bromine. Nitrogen is less than oxygen because oxygen is right next to fluorine. Alright, polarity in molecules. So electronegativity between covalent bonds, if they are the same, they are equally sharing, therefore they're nonpolar. They're basically, think of polarity as unequal sharing. If you have one side that's more than the other, then they'll be slightly polar. If they're equal sharing, like hydrogen, chlorine, bromine, even fluorine, if they're bonded to themselves, will act nonpolar because there's no difference in their electronegativity. There's no one side that's more positive than negative. How you determine types of bonds is basically understanding the difference in electronegativity. You can see here on the left side, if the equal sharing of electrons, that means the difference between electronegativity is between 0 and 0.4, it's a nonpolar substance. If you go between 0.4 and 2, or 0.5, there is an unequal sharing. You can see a partial negative, or that's going to be positive, and a partial negative. That means there is unequal sharing of electrons that are going to be polar. And then an ionic bond is a clear transfer of electrons. There's a clear positive and a clear negative, and it's a very strong bond. Alright, so two atoms partially charged, you're going to get a partially negative positive charge and a partial negative charge. Therefore, it has a dipole intermolecular force because there is a partial negative and partial positive. As the electronegativity increases, it becomes more and more polar towards ionic bonding, and that is the degree of polarity is measured by that dipole moment. So you can see here, hydrogen chlorine. Chlorine is very electronegative, has 6 unshared electrons. Hydrogen has 0, so it's going to have more partial positive on hydrogen, a partial negative on chlorine, and you have a polar molecule. You can see here again, dipole moment. Hydrogen is more positive, chlorine is more negative. Alright, here we got trichloromethane. This is a polar substance. Why? If you can see, chlorine has all the electrons around chlorine. There's 6 electrons. Now hydrogen has 0. It's being shared with the carbon. So all the electronegativity is towards the chlorines, leaving hydrogen be partially positive. On the other hand, you have tetrachloromethane. That means 4 chlorines. There's no unequal sharing. All have 6 valence electrons that are shared. They're pulling equally. Therefore, there's no unequal pulling, unequal sharing. So it's nonpolar. Alright. Quick checkup for your homework assignment. You are to determine if this substance is polar or nonpolar, and you need to justify your reasoning. A, you have chlorine molecule. B, hydrogen fluoride. C, the V-shape or bent-shaped sulfur dichloride. The D, the tetrahedral molecule of chloromethane, CH3Cl, and the tetrabromomethane, CBr4. Alright, polarity and chemical reactivity. So what is similar about these two molecules? You can see they have triple bonds. There's a lot of electrons here in the middle, okay, making triple bonds. The difference is what atoms you have. Carbon has 2 electrons here, oxygen has 2, nitrogen has 2, nitrogen has 2. So what's different about them is that oxygen is the most electronegative atom out of the three. Nitrogen is very electronegative, but they're equally pulling. Carbon isn't as electronegative as oxygen, so oxygen is going to have more of a negative charge. So it's polar. Nitrogen is not polar. So polarity plays a big role in reactivity. So it determines the chemical reactions that are started by a reagent attacking one of the electric charge ends. So you need to know which side is negative and which side is positive so you can determine how the reactivity is going to occur, especially in organic chem. Alright, van der Waals forces. So these are called temporary dipole induced forces, or London dispersion forces, these also can be called, but they're temporary. So temporary means that the positive negative charge moves, and this all depends on the electron. The electrons move throughout the atom, so they temporarily become positive on one side and then temporarily become negative on the other, and they keep moving around. That's why it's a weaker force, because there's no set positive and negative part of the atom, or the compound, sorry. So they hold molecules together, but they're very weak. Van der Waals forces, they increase when you increase the number of electrons and protons, and because there's more chance the electrons will be on one side and protons are going to be more positive. More protons mean more positive, so you can have more attraction. So increased weight helps increase the contact points, so where the places the molecules can come together, helps a stronger attraction. So increase in protons and electrons, which increases the contact points on the molecule. So here we have helium. Helium only has 2 protons, 2 electrons, so very light. Argon, on the other hand, is a gas as well, but it has a higher boiling point, a higher boiling point than helium, and a higher melting point if you get to a solid, because of the number of protons and electrons. So argon would have a stronger van der Waals force than helium. Therefore, it would have higher melting point and boiling point than helium. So bigger the molecule, stronger the van der Waals forces. You can see this from the chart. You have the noble gases, the enthalpy of vaporization, so how much energy to vaporize the liquid. So you can see helium is very low, and as you go up the periodic table, you are increasing the energy of vaporization as well as the boiling point, because you have more electrons, means more protons, and you have more chances of contact between molecules. So again, why does the enthalpy and boiling point increases? It's because of the energy needed to change the liquid to a gas is higher than when you have less protons and less electrons. All right, VDW, or van der Waals forces, their vaporization and boiling point, the increase of the number of electrons, more energy to change to a liquid to a gas, and a higher boiling point. Alright, you can see here pentane and 2,2-dimethylpropane. You can see which compound you think is going to have a higher boiling point and why, even though they have a equal number of electrons. The carbons in dimethylpropane are more clumped together. Therefore, there's less contact between the other carbons of the molecule. So if you were to make contact with another molecule, you only have a couple places in diethylpropane, but here in pentane you can line them up and have more contact with the carbons. So pentane is going to have have a higher boiling point, melting point, due to the more contact points of the pentane molecule. So more contact points means van der Waals forces are higher, higher boiling point, and such whatnot. Okay. So permanent dipole-dipole forces. So this means that there is a clear difference in electronegativity. One molecule is going to be, one part of the molecule is going to be more negative than the other part of the molecule, which is going to be more positive. It's not as strong as ionic compounds, but they're stronger than van der Waals forces. So you can see here in propanone, which is a ketone, has oxygen, which has 4 electrons in the outer shell, which causes it to be more electronegative, which pushes carbon to be more positive. Molecule with a positive and negative end is due to unequal sharing because of electronegativity. Oxygen is more electronegative than carbon, so it has a permanent negative charge. So small molecules with the same number of electrons. The permanent dipole is greater than the van der Waals forces because of electronegativity. So you can see here they're the same molecular weight, butane and propane or propanone, but propanone is a higher melting point and boiling point than butane because of the dipole-dipole forces by the carbon and oxygen. Butane's at 0 degrees Celsius, propanone's at 56 degrees Celsius because of the dipole-dipole forces. So it needs more energy to break propanone than it is to break butane. You're not breaking the molecule, you're just separating the molecules from themselves. Dipole-dipole strong enough to make propanone a liquid at room temperature. But butane, like a lighter, is a gas at room temperature because of the weak van der Waals forces. Alright, homework question number 2. Bromine and iodine monochloride, ICl, have the same number of electrons, but the boiling point of ICl is nearly 40 degrees higher than the boiling point of Br2. Explain this difference. Alright, hydrogen bonding. So hydrogen is a very strong intermolecular force. It only deals with 3 atoms. Well, obviously hydrogen. And when hydrogen is bonded with fluorine, oxygen, and nitrogen. So you're talking about hydrofluoric or hydrogen fluoride, you're talking about water, and you're talking about ammonia. So, why do these strong hydrogen bonds only occur in F, O, and L? You gotta go back to the periodic table and electronegativity. Fluorine's most electronegative, then oxygen, then nitrogen. And the reason why they're most electronegative is because of their radius. The radius between the protons and the electrons cause the radius to shrink, so you can have a strong bond and a strong partial negative and a partial positive on your atoms. See here, ammonia has 2 electrons, 1 lone pair, causing the negativity to be on the part of nitrogen, causes the H's to be positive, and there's a strong attraction between a positive and the negative electrons. See, same with water. Water is very electronegative. It has 4 electrons. Therefore, the partial positive is in the hydrogen area. So you can have a strong hydrogen bond between H and O. Same with ammonia, you can see here. The negativity is in the lone pair. The positivity, is that a word? Sure. Is in H. Hydrogen bonds very strong, increased boiling point of the molecule. So here are boiling points of hydrogen halides, hydrogen halides, with the highest being which one? HF, HCl, HBr, HI. If you said HF, you are correct because of the hydrogen bonding. Now, you notice after HCl, it starts to rise, and that's because of the size of the atom, compound. All right, homework question number 3. Here you have 4 group 5 hydrides: ammonia, phosphine, arsine, and stibine. Explain the trend in the boiling points from phosphine to stibine, and explain why the boiling point of ammonia does not follow this trend. All right. Last part is particular properties of water. Water is very unique, especially when it freezes. So enthalpy change and vaporization and the boiling point are very high due to hydrogen bonding, which is good. So you can see here that the vaporization of group 6 hydrides, that'd be oxygen, silicon, and so forth. Hydrogen and oxygen would have the highest, water. And this is going to be very similar to the halogens with sulfur, selenium, and then tellurium. Surface tension and viscosity of water. Again, the reason why they have high surface tension and viscosity is because of the hydrogen bonding. It allows molecules to slide and exert certain force downward from the surface. That's why you get that bubble. If you were to put drops on a coin, it would be a concave down. Ice is very unique. When water freezes, it actually makes a rigid lattice, which allows air to be kind of surrounded in a tetrahedral shape and spread out, so it makes it lighter. As you can see here, the hydrogen bonds form a space